The strong nuclear potential well. Let's summarize what we have covered in the previous lecture. So just a very brief summary. We found here that nucleons greater than D greater than D critical do not experience the strong attractive interaction. If nucleons are close to the critical point, there is an attractive interaction. And then finally, if nucleons are inside D critical, the strong force grips the nucleons tightly and binds them to the nucleus. That's what we effectively did in the previous lecture. So now what we want to do is that we want to look at the strong potentials for the neutron and the protons. So let's start with the strong potential. And you're going to see that the word force doesn't make sense in this language. We really need the potential to really explain. So we're going to start off with the strong potential for protons. So a proton fired at a nucleus shows certain behaviors. So let's start off with what we have seen. We know that there is Coulomb repulsion, and we know that there is strong attraction. So if I shoot a proton, okay, here's my proton. So if I shoot this proton in this direction, and I have a nucleus here, there's going to be two motions. There's going to be a motion that's going to be in the so if I'm exceeding the critical distance, I get Coulomb repulsion. But if I'm about or close to around the critical distance, I'm going to see strong attraction. So how do we show this in our potential curves? So because these are complicated to draw them out, I'm going to try to, I'm going to copy some of these and carry them forward. So I'm looking at this guy, and this is what I'm seeing here. So if I was to draw the whole thing out, I'm going to get a curve that looks like this. And these guys should be smooth. And then I get a little tiny bump right here. So when I'm looking at this, all this lime green that I'm drawing here, this is the forbidden region. And if I draw this, just this by itself, I'm going to say that this here, this is my 2 Fermi point. In other words, this is what I call D critical. Now, when I'm looking at this, this has a lot of terms. So this is our symbol for the potential function, but it includes numerous terms. So I'm going to say that this is the effective potential. And I'll show you what that means now. Now, I'm going to do the exact same thing, but I'm going to fire a proton at this. So what you're seeing here is that if I fire a proton, what actually happens? I shoot this proton, and you can see here that there's this little bit of a hill. This little bit of a hill here shows me that right there, this is what we call Coulomb repulsion. And you know what? I said I wanted to copy this. So I'm going to copy this because I'm going to need it later. And in fact, I'm going to put it right here, and then I'll come back to it and get it later on. Do I need this later on? I don't think I'm going to modify this. So I'll leave it there for right now. So now, what do I see? I have Coulomb repulsion, and then look at what happens here. If I'm going to get any bending here, look at where the proton is at. Right here, I have the proton coming in, and as it comes in, you see how there's that downward slope. So right here, what you're seeing here, this is my strong attraction. And again, because it's speeding up, so that means that the force and the direction are the same. Once a proton is captured and it's in the well, you can see here that now this is what we are now calling a bonded proton, a bond proton, or bonded, I should say, proton. But this is a complicated potential. It turns out that protons have this thing called intrinsic spin. And right in here, you see here that it gets, the potential starts to be very, very steep right there. This is due to the Pauli exclusion principle. So this potential has a lot of details here. Okay, so now I'm going to do the exact same thing, but now I'm going to go and look at the strong potential for neutrons. So what we know with neutrons that if a neutron fired at a nucleus shows two behaviors. So one of the behaviors is that, again, if I was to copy this, and then I'm just going to copy it down here, what I'm seeing here is that I get this. There is no Coulomb repulsion, right? There is no Coulomb repulsion. So when I'm looking at this, if I fire a neutron, it does follow. But over here, we see that there is no Coulomb repulsion because neutrons don't have any charge, but they do experience a strong attraction. So now what I have to do is that I want to take this picture right here and I want to modify it. So I don't have to copy it. Actually, I can just bring it down here. So if I do the same thing here, what actually happens now? So the way I'm going to modify this is that there is no Coulomb. So I have to kind of modify this a little bit because it now goes effectively to 0 right away past 2 Fermi. So if I look at my neutron, it's coming in and it's going straight. The potential is flat. So we start to experience the attraction about right here. So here, what you're seeing is that right here, we're getting strong attraction. That means if I fire it and it's at that distance, it's going to have this curved trajectory. But if it's in the well here, then we're going to say that this is a bound neutron. The neutron is now captured. And as before, we've already said here that this is all, again, this is the same thing as before, which is the Pauli exclusion principle. So the wells are identical, but but outside between the proton and the neutron, there is that Coulomb that we have to look at. So now let's write some details about this. So let's start to interpret the details. So the first thing here is that note the attractive strong potential is the same for both proton and neutron. And the reason for this is that the strong interactions do not distinguish between nucleons. They don't tell the difference between a proton and the neutron. However, the proton does experience Coulomb um, experience, maybe I should say a Coulomb interaction when it's outside D critical, which is exactly what we were talking about. These potential wells are tricky, and there's a lot of details, so we need to start to simplify these things. So that's what we're going to do now. So the depth of a potential well is the binding energy which I typically write as Be. This is also known as the ionization energy. So the language, I should be a little bit careful here. If we talk about removing electrons, it's called the ionization. If we're talking about removing nucleons from the nucleus, then it's called the proton separation or the nucleon separation energy. So, but let's keep moving along this direction here. And the first thing that we should say here is that the electron binding energy for atoms is caused by the electric charge of the nucleus. Its depth is about 10 electron volts. Again, that number doesn't necessarily have to mean very much. So if this is the case here, what do we know about nucleons? The nucleon binding energy for nuclei is the cause, excuse me, let me be careful. That is caused by the what they call color charge. Its depth is about 10 million electron volts. That's 10 to the 7 versus 10 to the 1. So it's really, really deep here. So we say here in the language of binding energy, the nucleus that creates the strong potential well is a million times deeper than electric potential wells by nuclei. And that has to do with the force. So if I was to think about this picture-wise, I can't really compare a million times difference. So the way we want to do this is that we want to start to simplify our picture. So my picture here is I'm going to say, well, I have a little tiny well right here, and I'm going to put an electron in that well. And so what I really see here is that this is my forbidden region. And if I measure this depth right here, from here to here, we see that this little binding energy is about 10 electron volts, where inside at the bottom of the well is the electron. This would be the, how would I call this? The electric potential. Now, if I compare this to the nuclear ones, they are much, much deeper, considerably deeper. So when I'm looking at my well, again, they also have forbidden regions. And there's two wells that are binding nucleons. So remember, they're not approaching it. They have now been captured in the nucleus. So my picture of the nucleus would be something like this. So if I have a potential well, then that tells me that that's the proton well. If I have a neutron down here at the bottom, that right there is my neutron. And you could see that the well has the same depth because it doesn't distinguish between them. So when I look at this depth here has a much, much larger at essentially 10 millions electron volts. So these guys are the strong potential wells. So once again, we talked about binding energy a little bit, and we said it here, it's like the ionization. So let's properly define this here. And we say this, the process of removing particles, let me be more specific, electrons from electric potential wells is called ionization. And ionization is essentially the work to remove the electron. And I can say the exact same thing for nucleons. The process of removing nucleons from the strong potential is called the separation energy. And you could see that that separation energy turns out to be 1,000,000 times stronger. So when we're looking at what charges participate, we're finding here that electrons have low ionization energies and will participate in electron and charge transfer. On the other hand, nucleons that are inside the nucleus require extremely high separation energies of the order of 10 million electron volts. And these guys will not participate in everyday situations. We'll look at this more a little bit later. So the last thing I want to cover here is overcoming the strong attraction. The question that is really being asked here is that why are some nuclei stable and others not? Why are some nuclei stable while others are not? The answer lies in the competition between the attractive, strong versus the repulsive electrical forces. Now, before I can answer that, we need to understand a little bit more about the nucleus. So we need one more detail about the nucleus. And this involves the density of nuclei. So let's look at this thing here. As one increases, the number of nucleons its radius increases, but its nuclear density remains fairly constant. And that's surprising. So let me show you what I have here. So I have this image here, and we're plotting the density with reference to the radius here. So when I'm looking at this, I'm going to say that if I look at this region right here, right? So if I'm looking at this region right here, you're seeing that this distance is about, this is about the middle, not the middle, but it's the center of a nuclei. And so if I was to try to put this into words, I would say that the middle, the center, has a constant value. It's not exactly right, but if you look, so you can see that there are four ones. There's calcium, cobalt, iodine, and gold. So if you look at the last three, their densities are very similar. But calcium is much smaller, but you could see that it still has a fairly constant value to the whole thing. So the center has a constant value over a wide spread of nuclei. But what you find here is that when you get to the edge right here, let's focus on cobalt for right now. But if I focus on cobalt, look at that. Cobalt decreases fairly quickly to zero here. So in other words, the edges of, excuse me, at the edges, one sees a quick drop off. So the density goes to zero very fast. So here we go. It turns out the edges of a nuclei turn out to be their Achilles heel. It's their weak point. Here's why. The maximum range of the strong force is 2 Fermis. And because of this, it's called the nearest neighbor force. Since 2 Fermis is an extremely small distance. So I want to visualize this thing. So to visualize this, Let's use an analogy. And here we go. So here's my analogy. So when I look at my analogy, here's what I want you to think about. Imagine that we have so suppose a collection of Velcro balls. In other words, the Velcro produces an attractive force. So the attractive Velcro force is a nearest neighbor force. Okay, it's a nearest neighbor force since it can only make contact, it can only make contact with nearby Velcro balls. So let's start to look at this thing. So picture-wise, I'm going to say that I have a blue ball in the center. And I take this ball, and it has Velcro all over the place. Now imagine that I have green Velcro balls that look like this. So when I'm looking at the range here of the Velcro, it can only make contact, right? So this here, what you're finding here is that this is a short range force. In nuclear physics, we call it the nearest neighbor force. On the other hand, now let's look at other not tennis balls, but Velcro balls. Now imagine that we have orange ones and they're connected like this here. So what you're seeing here is that when I look at this orange ball right here, this orange Velcro ball does not feel a force from the blue Velcro ball. It has to be in contact for the Velcro to stick here. So now so if I look at this thing, then I could come over here, and if I look at this, I'm seeing that there's only contact with two green balls. So let's be careful about the magnitude of the force. So now let's look at the magnitude of the attractive Velcro forces. I would say that the inner blue ball interacts with 6 green Velcro balls And if I look at the orange one, I'm going to say that the surface orange ball interacts with two green Velcro balls. So what you're seeing here is that the inner blue ball has maximum Velcro force. In this situation, we're seeing that this has a much reduced Velcro force. So now what we really want to look at is that we want to look at what does that tell us about the binding energy? If we have maximum Velcro force, that means this experiences maximum binding energy, where this guy has a smaller binding energy. It's the surface nuclei in, it's the surface nucleons and nuclei that is the Achilles heel, just like this. So if I'm going to remove a blue ball, I'm going to have to work a lot harder. Why? Because I have to deal with 6 green Velcro balls. They're holding it tighter compared to the orange one. The orange one only has 2 green balls, so that's a much reduced force that I have to apply. Or we say that it's binding energy. So here we go. The surface nucleons of a nucleus are the Achilles heel of the nucleus. And this is the reason why. The strong force is a nearest neighbor. In other words, that's what we mean by a short range, whose maximum range is 2 Fermis. Since there is less strong attraction on the surface nucleons, these are weakly bound. The repulsive the repulsive electrical force between protons is a long range force, and that means force that extends well beyond the edge of the nucleus. In fact, the electrical force is an infinite range force. So now we can address the issue of an unstable nuclei. The issue of an unstable nuclei. So let's do this in 4 steps. And the first step here is this. As more and more nucleons are added to the nucleus, it increases in size and creates more surface nucleons. This causes the attractive strong force to decrease in strength. Two, as more nucleons, and in this case, we really need protons, as more protons are added, the nucleus does increase in size, but the electrical repulsion also increases too. In other words, this causes the repulsive electrical force to increase in strength. So they're doing the opposite things here. As it gets larger and larger, more surface nucleons are created. Therefore, there's less attraction around the edges. The nucleus starts to reach a critical point. At some point, a critical point is reached. When nuclei reaches uranium, there is a critical balance between both forces. So the atom that we're talking about here is atom 92 with an atomic mass of 238. This has 146 neutrons and it has 92 protons. So when I'm talking about a balance here, I imagine that I have a fulcrum right here. And then I have my balance situation. So when I'm looking at this, I'm seeing this. Over here, I have the strong force. And on the right side, I have the electric force. These two at this uranium atom are critically balanced. In other words, we could then say that F strong is essentially being balanced, just barely being balanced, because these guys are effectively neck and neck. So now we make our last statement. Uranium is the last natural occurring element. If one more nucleon is added to the nucleus, the electrical repulsion becomes larger than the attractive strong force. In practice, what you do here is that you send in a slow moving neutron that gets captured by the uranium nuclei. This causes a fission process, and it goes something like this. So I'm going to start off with a neutron. So I'm going to shoot a slow moving neutron. In fact, there's a name for that. It's called a thermoneutron. Now I have an atom or a nuclei, and this guy is, we're going to shoot for 235. So now what happens? If this neutron is just right, this is called a neutron capture. And in this process, it absorbs that neutron. And if it absorbs it, here's what you find. That this goes to 236 uranium. And this guy is extremely unstable nuclei. It's extremely. And immediately what it does here is it goes through a fission process. And as it goes through a fission process, it goes through a complicated process, but effectively what ends up happening is that you have a model called the liquid drop model, and you get two parts that now start to oscillate very quickly. But what you're finding here is that some of the protons are here and some of the protons are over here. And these guys just start at super high speeds. And then what happens here is that you get this is what they call the splitting of the nucleus. We don't call it an atom bomb. That is wrong. We do not call it an atom bomb. And so what happens is that these pieces effectively stretch and they move in different directions. So I get a very strong electrical repulsion going this way, that way. And so if I'm looking at this, what do I say to myself? Then you're going to find out that there is this intense energy that's released here. So this has an extreme electrical repulsion. So in summary, splitting a nucleus like a nuclear bomb so in summary, splitting a nucleus is the basis of a nuclear bomb. The fission process is a way to release the pent up electrical repulsive energy stored by the attractive strong binding energy. Therefore, a nuclear bomb is really an electrical ball.